So today we're going to talk about cylindrical coordinates. We're going to talk about what they are, how to convert between rectangular and cylindrical, and then finally we'll look at how they help us with triple integrals. So here's the idea with cylindrical coordinates. They're nothing that new. Cylindrical coordinates are just polar coordinates, but three-dimensionally. So it's when you extend polar coordinates to 3 dimensions instead of 2. So here was the idea two-dimensionally. You would go over x, and then you would go up y, and that would be your point. So over x, up y. The idea with polar, then, is that we would go over theta and out r. So our point in xy, we re-expressed as a point in terms of r and theta. Here's the idea three-dimensionally. Okay, so in rectangular, you would go out x, and then you would go over y, so out x over y, and then we would go up z to find some point here. So out x over y, up z. Okay, here's the idea then in cylindrical coordinates. The idea in cylindrical is you first do your r and theta. So here would be my theta. Here would be my r. So I have my rotation of theta out of r. So that's the same as polar and two-dimensional, but then I just go up z. So rectangular is x, y, z. Cylindrical is r, theta, z. So r and theta is two-dimensional. So you do your rotation, you go out however far the radius is, and then you go up z. Can we picture that? So do we see why it's called cylindrical? It's like working on a cylinder. You go out the radius, you go over the rotation, and then you just go up. So it's like you're working on a cylinder. Okay. Converting, you already know how to convert because it's just like polar. If we are going from cylindrical to rectangular, so if we have the r theta z, how do we get that to be rectangular? X is r cosine theta, y is r sine theta, and then what's really nice is z is just z. Z you don't have to convert. You also have to be able to go the other way, from rectangular to cylindrical. So if you have x, y, z, how do you get that in terms of r theta z? We know r squared is equal to x squared plus y squared. Tangent of theta is y over x, and then again z is just equal to z. Okay, so first example. Part A, we are going to plot the point 2 pi over 3, 1, and find its rectangular coordinates. So we'll plot and then we'll find the coordinates. I'm going to do the theta first. So theta is always from the positive x. We'll be rotating 2 pi over 3. So that puts us somewhere over here. Once we're over here, we'll be coming out a radius of 2. So this is still on the XY plane. It's hard to draw it in perspective though. And then we'll be going up 1. So that is our point. So rectangular coordinates then, x is going to be r cosine of theta. Y is going to be r sine of theta. And z is just z. Cosine of 2 pi over 3. Negative 1/2, so multiply by 2 will give us negative 1. Which should make sense. We can see that x is going to be negative. Sine of 2 pi over 3 is root 3 over 2. So that is our point in rectangular coordinates. Make sure that your point makes sense. So we know that x has to be negative. We know that y and z are positive. We good so far? Yeah. Okay, B. This time we are going to find the cylindrical coordinates for a point. Our point is 3, negative 3, negative 7. Okay, so r is x squared plus y squared. So I'm going to do the square root of x squared plus y squared, which gives me 3 root 2. Tangent of theta is y over x, so negative 3 over 3. Okay, here's where we need to be careful. Tangent of theta is negative 1. Where does that occur? Three pi over 4. Where else does it occur? 7 pi over 4. You have to consider the figure to determine which one is the correct value. And then z is just z still. So we know our point is going to be 3 root 2. So that's our r. Something for theta, and then negative 7. Okay, well, consider your figure, or this point. I would go positive 3, negative 3, negative 7. So is my theta 3 pi over 4 or 7 pi over 4? 7 pi over 4. Do you all see why? Yeah, we're okay with that? Okay. Do we feel comfortable converting? Okay, great. Before we do anything with triple integrals, you also need to know what different equations look like. So we are going to describe the surface. Z equals R. Okay, so if z equals r, well, r we know is the square root of x squared plus y squared. So if we look at this in rectangular terms instead, what is this? That's the cone. Yeah, this is definitely a cone. For different values of z, we get a circle. So, something like this. It's not the bottom cone, though. It's just the top one. Because z is going to be positive. Okay. Now, similar to when we did polar, we saw when we were doing double integrals that sometimes it was easier to compute a double integral using polar coordinates instead of rectangular. Same is true with triple integrals. Sometimes it's easier in rectangular, sometimes it's easier in cylindrical. So that's what we're going to look at now, is the triple integrals. Okay, so one thing that I want us to recall is that we were looking at the triple integral over some solid E, and we were integrating a function. And we talked about looking at this like it's a Riemann sum. Okay, and then we said that that delta V sub k is going to be the area of the base times the height of each parallelepiped. From earlier, delta V sub k, area of the base, so when we did this two-dimensionally, the area of the base was r of k star, delta r of k, delta theta of k. The height is delta z of k. Here's what that tells us then. If we are looking at the double, or rather the triple integral over some solid E, if I convert this to cylindrical, so I have my function now in terms of r theta and z. Do you remember what you had to do when you were doing a double integral and you converted to polar? Multiplied by r. Cylindrical, exactly the same. So you multiply by r, and then generally you do dz, dr, d theta. So remember, you need the r. Okay. Questions? Great. Okay, I want to talk about how to determine limits before we look at examples. Okay, so remember how with triple integrals we looked at a bunch of different examples where sometimes you integrated with respect to z first, and then sometimes y, and sometimes x? Cylindrical, you're always going to integrate with respect to z first. So the first thing that you want to do is you want to identify your upper and lower surfaces. Your upper surface is going to be z is some function of r and theta. And your lower function, or your lower surface, is also going to be z equals some function of r and theta. So that's nice about cylindrical. Next, you are going to make a 2D sketch of the projection onto the xy plane. And that is to help you determine the bounds for r and theta. So we are going to evaluate triple integral over the solid G dv, where G lies within x squared plus y squared equals 1, below the surface z equals 4, and above z equals 1 minus x squared minus y squared. Okay, before we draw a picture, because like before we're going to need a picture to find our limits, what are we finding? Just volume, because it's 1 dV. So we're finding a volume. Okay, we need to draw this figure. Okay, z equals 4. It's going to be some plane up here. I'm not going to draw it yet, but you're going to have a plane up here that's cutting us off. Z equals 1 minus x squared minus y squared.
Paraboloid. No, never mind.
It's paraboloid. Some paraboloid that keeps going down. Okay. X squared plus y squared equals 1.
Circle. That's the... Oh, in 3 space. Sorry. Oh, is it a circle?
No.
It's a
Cylinder.
Okay.
Oh, guys, come on. X squared plus y squared equals 1. On the xy plane, it's a circle, but then we're saying z doesn't affect anything, so you're just taking that circle and moving up and down the z-axis. Oh, okay. Feeling very confident. Okay. So we are finding this volume here. It's like you are taking the cylinder from the xy plane up to 4, but you're removing like that bump at the bottom. Okay. So I want us to set this up in rectangular. In this case, we have a lower surface that z equals and an upper surface that z equals, so I think it makes sense to integrate with respect to z first. Z goes from 1 minus x squared minus y squared up until 4. What is our region R then? So what do we need to look at to find the bounds on y and x? What is our projection onto the xy plane? Yeah, circle. So we're going to look at this circle right here. So if I take that circle and I solve for y, y is going to go from negative the square root of 1 minus x squared to positive the square root of 1 minus x squared. And x will go from negative 1 to 1. Now, could you integrate this? Certainly. Probably not the easiest way to do it, though. So what we're going to look at now is what this looks like if we convert it to cylindrical. So it's still a triple integral. You have to remember to include the r. And then convention, like I said, is to do dz, dr, d theta. I don't think I've ever done it in a different order. So at least 97% of the time, this is the order that you're going to do. These are pretty easy to convert to cylindrical. 1 minus x squared minus y squared is just 1 minus r squared. 4 is just 4. R goes from 0 to 1. Theta goes from 0 to 2 pi. Okay, can I split this up into multiple integrals? No. What is the issue? 1 minus r squared. Okay. So this is the only one I have that we're actually going to go through all the computation for. Sound good? Great. Let's do the computation. Okay. So we're going to end up with z times r. Z is going from 1 minus r squared to 4. So I have then 4r subtract r times 1 minus r squared. I have 4r subtract r, so that's going to give me 3r. Add r cubed. So now integrating with respect to r, I get 3 over 2 r squared plus 1/4 r to the 4th from r equals 0 to r equals 1. So this is the integral from 0 to 2 of 7 over 4 d theta. So we'll end up with 7 over 4 times 2 pi, which is 7 over 2 pi. Okay, hopefully we can see that evaluating in cylindrical or integrating in cylindrical is much nicer in this case than rectangular. Questions on this one before we go on? One thing I want to point out to you. You guys know from your test that I grade pretty harshly, and I expect you all to have proper notation. You need to have parentheses here to show that everything is being integrated with respect to r and theta. If you do not put parentheses on your exam, I will take points off. Is that clear? So now that I've told you, I don't want any whining later when I take points off. Jelly?
I know you said you highly recommend writing r equals 1 or r equals 0.
Yep.
You just write 1 and 0. Are you going to take a point off?
No. Okay. We're going to do 2 more just setting up. That was the only evaluating one because evaluating is the same as what we've been doing. Okay. Next example. Here's the triple integral that we are looking at. X squared plus y squared to 2, negative the square root of 4 minus x squared, positive the square root of 4 minus x squared, and negative 2 to 2. And then our integrand is x squared plus y squared dz dy dx. Okay. My expectation for you is that you see this and think maybe there's an easier way. Here's what I want you to do. If you look at these 2 limits right here, what is that? That's a circle. Yeah. So as soon as you see that that's a circle, that should tell you it might be easier to do this in cylindrical. X squared plus y squared is going to turn into r squared. As soon as you convert this to cylindrical, you need an extra r. And then we have dz dr d theta. Z, all you have to do is convert the bounds to cylindrical. So the square root of x squared plus y squared, that's just r. 2 is just 2. Now, you can either sketch this r, or hopefully you can tell that it's just an entire circle with a radius of 2. So r goes from 0 to 2, theta goes from 0 to 2 pi. Okay, we're not going to go through all of that calculation. If you care, the answer is 16 pi over 5. Okay. Ready to do one more? Wonderful. Last example. We are going to let E be the region inside the sphere that has a radius of 2, and that is centered at the origin. And E is above the plane, Z equals 1. What we are going to do is find the volume of E. Okay. I want to give you like 2 or 3 minutes to try this one. So I don't want you to go through the calculation. All I want is you to set the problem. whenever you're ready, turn to the person next to you and compare, please. Okay, are we ready to start chatting? Okay. This is what I have so far. So this is the region that we're trying to find the volume of. Our z then is going from this plane to the surface. So it goes from 1. You have to solve this for z. So we get z is the square root of 4 minus x squared minus y squared. So this will be the square root of 4 minus r squared. Hopefully you remembered your r here. This is what I think is more difficult, is the region now that's left, or the projection. R does not go from 0 to 2. This is not the projection here. So you got that? Not great. This is the R. This circle here, that'll be projected down onto the xy plane. Now, to figure out what that is, you have to figure out where your surface intersects with the plane. So to find d, we get x squared plus y squared. In this case, z is 1. So our region D, or R, I use both, is x squared plus y squared equals 3, that circle. So our R goes from 0 to root 3, and theta goes from 0 to 2 pi. Okay, if you didn't get that, that's okay. Hopefully we now understand why that's the case. That's all I have for us. How do we feel about cylindrical coordinates? Not too bad? Okay.